Okay, so let's do some more questions about fluid mechanics, including statics and dynamics for the MCAT, typical questions for the MCAT. And some questions are easy, some questions are not that easy, but let's go over them. So you should pause the video first, right? And try to do that on your own. So let's try to do the first one. Here. So pause the video and try to do this. Okay, so you have two substances and density. One is twice the density, has a density twice. So they are asking the pressure beneath the surface. And they want that pressure to be the same for both cases, right? So they are referring to hydrostatics pressure. So that will be hydrostatic pressure, and you have delta P, okay? Delta P is proportional to height and proportional to density. Okay, and of course it depends on gravity, right? So it means that if you multiply the density by 2, okay, so delta P will also be multiplied by 2 for the same delta H. So it means that you have delta P, which is the hydrostatic pressure, right? So the difference in pressure for a difference of height delta H, okay? It's proportional to the density and proportional to G. So this is also called the gauge pressure. So they are talking about the pressure beneath the surface, so delta P. So at the surface, maybe it's the atmospheric pressure. So if the density is multiplied by 2, okay, so multiplied by 2 here. So if the density is multiplied by 2, okay, so substance B has a density multiplied by 2. So if you want delta P to be the same, okay, so this here should be divided by 2. So it means that B should be half. Whenever depth is 2 times, whenever the depth is, so density is multiplied by 2, so the height will be multiplied by 2 for A. So it means the depth for substance A is 2 times. Okay? So it means that if you have the substance here and you have substance A, so you need twice the height here relative to substance B. Half of that. Okay, so that will be delta H. So this is half of that because the density here is multiplied by 2. Okay, so that will be the answer. The answer is C. So let's go to the next one. So the most important is that you do it on your own. So let's do the next one, and you should pause the video. So pause the video here. So this refers to the definition of the pressure. So the pressure is a force. So if you have an area A, there is a force applied here. So the pressure is the force per unit area, or a force applied to an area A is the pressure times the area. Okay, so you can read along. So if you have a low pressure, so it means if the pressure goes down and you have the same area, okay, so the area is the same, so this is the same, this stays the same, so it means the pressure, the force is going to decrease. So low pressure, low force on the window. And the thickness doesn't matter, it's just giving you more information that you need. Okay. Now, to see that, you can say delta F over F will be equal to delta P over P times the area. Okay, so this, if this changes by 1%, that's going to change, the relative change will be also 1%. Okay, so A will be the answer. So if you multiply here by a factor of m, multiplied by m here, that will be also multiplied by m for the same area. Okay, so next question, again, this is good if you go to medicine to understand that, but it's a simple question. Blood flow, so the circularity system, so it's not always the same volume, right? Sometimes it can flow faster, sometimes it's going to flow slower, but at least the thing that we are sure of is number C, right? Because it's a conservation of the total amount of blood in the system. So whatever comes out has to comes in. So C will be the answer. Okay. So let's try to do this one here. You can pause the video again. So you have the same mass and they are submerged, and the sphere C is larger than sphere Y, but they have the same mass. Which one will experience the largest buoyant force? So the buoyant force depends only on the weight of the water displaced. Okay, by definition, that will be your buoyant force here. So it's only depending on the weight of the fluid displaced. So in that case, they both have the same mass, okay, but mainly they do not have the same volume, right? So sphere X is larger in size, so it means it's going to displace more fluid or more water. So that means the buoyant force will be larger. Okay, so answer is A. Okay, so the buoyant force is the weight of the fluid displaced. So it's going to be fluid here, and they are totally submerged. So it's the total fluid volume, the total volume of the object times G. So if this is larger, that will be larger also. And the factor here will be the same. If the volume is multiplied by 2, the buoyant force will be multiplied by 2. Okay, so that's an easy question. So let's go to the next one here. So here you have a hydraulic system. So they want you to apply Pascal's law. No, I don't know if I have a slide. I think I have a slide, but okay. Here, it's called Pascal's principle. So Pascal principle says that the pressure here is transmitted to all points in the fluid. So it means the pressure that you get here, that's applied here, will be the same as the pressure over there. And pressure is force per unit area. Okay, so for example, here you have F1 times divided by the area, because that will be the pressure. So the pressure here equals to the pressure there. Okay, you can see that here. So you have for the unit area, you're going to have the same pressure. Unit area, you have the same pressure. So of course, if you increase the area, you're going to increase the force. So this is the idea behind the hydraulic system. Okay, so the equation for that is you have F1 over A1 equals F2 over A2 if it's in the equilibrium. So it means so if you have a load here, so that will be the load. So the load here, it's going to have the force here, F2, and the area is A2. So just plug it in, right? So F1 is 4 over 16 equals the force here is X over 64. Okay, so X equals 64 times 4 over 16, which is 64 divided by 4, which is 16 Newton. So the answer is 60 Newton here. Okay, so again, this is called Pascal principles. Okay, you have the relationship here. So that comes from the book Johnson and Cantnell Physics, which I recommend for the mcat, and you see you have problems like this. Johnson and Cantnell. Okay, so this one is a little bit more challenging. So again, you can pause the video. Okay, so you need to understand what's hydrostatic pressure, also called the gauge pressure. So it's relative to the atmospheric pressure. So you can pause the video. So sometimes they give you more information that you need. Let's see what's going on here. So first of all, it says the density is 2 grams per cubic centimeter. So specific density is 2. Okay, because the density of water is 1 gram per cubic centimeter. So that means the density here is twice the density of water. And the density of that fluid is 1.33. Fluid here is 1.33. But you see that 2 is larger than 1.33. So that object here is sinking. So, and then it says immersed. So you can think of that as being at the bottom here. So you have your object here and it's totally immersed. Okay, so it's totally at the bottom. What is the total pressure acting on the submerged object? And here you have the atmospheric pressure here from the air column, which is about 100 or 101, about 100. It's about 101 or 100 kilo Pascal. And you see they give you the unit in kilopascal. So already this one is, if they want the absolute pressure, this doesn't seem right. So anyway, so the pressure is going to increase here on the object because of the hydrostatic pressure. So delta P here will be rho of the fluid G and the height, which is 25. So we have delta P equals, the fluid here is 1.33, okay, relative to water. The water is 10 to the third, okay, so water is also 10 to the third kilogram per cubic meters, and we need kilograms if we want Pascal. So 1.33 times 1,000, and then you have G, which is 10, and then you have 0.25. Okay, and if you do the computation, it's not that hard. Okay, you can do it by hand, and you're going to find about 3.3 kilopascal. And it should be capital, sorry. Okay, but they say the total pressure. So it means the absolute pressure. So it means this pressure plus that one. That was the trick here. So the pressure will be the atmospheric pressure plus your hydrostatic pressure. So it's going to be about 104 kilopascal. Okay, because you need to add the atmospheric pressure. Right? So this comes from my playlist about fluid. Okay, so let's do the next one. So this one is easy. You can pause the video and you can remember the equation of continuity. So if you have a large area here, so if it's the same fluid, not the same fluid, but the same mass flow rate or volume flow rate, okay? So every second you have the same volume flowing through, then you need to have this equation. And if the density is the same, so you have the same volume flow rate, right? If the density is not the same, so it will be the mass that will be the same flowing per second. So anyway, if you increase the area, the speed will decrease. If you decrease the area, the speed will increase. Okay, so you have this relationship here. So let's go back to the equation. So the answer will be capillary network is smaller. Okay, so the cross-sectional area of a single capillary is considerably smaller than the cross area of aorta. So the answer will be D. Okay, so this one is a typical question, and it takes you to Bernoulli equation. They want to find out so you have like a pipe, so fluid is flowing through, and where it's gonna flow here. So you have some speed, and now it's get more narrow, right? It's not as wide, so the speed has to increase, and then the speed will decrease again. So it's like a pipe, and then you have openings there. Okay, so it's a typical question, like if you look at if you use Bernoulli, you see that when the velocity is going to increase here, the pressure will go down. And you can see that here. That means here you have the atmospheric pressure that is balancing out the pressure from there. So the force will be in balance, but here the pressure will be less. So the atmospheric pressure can push more efficiently. So anyway, it takes you to Bernoulli. Where is Bernoulli equation? Okay, Bernoulli equation. So we don't worry about this. So Bernoulli equation is conservation of energy, because this is energy per unit volume. So that will be the potential energy per unit volume. So that does not change. But you have this here. So this is the kinetic energy that's from the static pressure. It's like work done by the fluid. So anyway, when the pressure goes down, the speed goes up. Okay. So that's the Bernoulli. Okay, you see you have a fluid flowing in this pipe here. Now, that's a larger cross-section. So you have some pressure here that keep those bubbles tight. And as the fluid goes faster, because the cross-section is decreasing here, so that's the continuity equation, you see the pressure goes down. So the speed goes up, the pressure goes down. So it's inversely. The relationship is inverse. Okay, so let's go back to here. Lowest will be 2. So pipe number 2. So that was a good one. Okay, so let's go to this one. So this one is just a quantitative question to see how fast you can do the computation without going into converting too much. Okay, so here they want you to apply again the continuity equation here, right? So area times the speed equals area times speed. But you have to remember that area is proportional to the radius square or to the diameter square. Okay, so in that case, if I want to go faster, I can say, okay, area 1 V1 equals area 2 V2. But area, of course, area will be pi times the diameter over 2 square. But because you still have pi on both sides, you're going to have 1 over 4 on both sides. I'm just going to write the diameter square. So on one side, you have 0.15 square times 8 equals 0.2 square times V. So that way, it's going to make the computation easier. So I can do 0.5 over 0.2 square times 8 equals V, and you need to find ways to make it easier to compute. So you can multiply by 100 here. So it's going to be 15 square over multiply by 100 here. It's going to be 20 square times 8. You can simplify your 2 and 2. 2 times 2 is 4. So it's going to be 15 square times 8 over 100 divided by 4. Okay, and I divided by 4, so it's going to be 15 squared times 2 over 100, so times 2. Right, I'm doing it in my head, and you get about 4.5. 4.5. Right. So the answer is C. And you should pause the video, of course. So let's keep going. So you have two wooden sphere that are submerged. So submerged means it's at the bottom, right? One has a density 0.5, the other one has a density 0.7. So both of them has a density smaller than the density of water. So if you're holding them, then if you let go, it's gonna rise because the density here is smaller than 1. So if it's rising and the net force is larger than, the net force is not 0, so it means the buoyant force is larger than the weight, so it will accelerate up. And you can see that the answer will be A, right? But you can make a drawing too. Okay, so it's submerged, but you have to hold it, right? You have to hold it because the density is smaller than 1, so it wants to rise. So it means the buoyant force here will be larger than the weight. And the weight is mg. So in both cases, the buoyant force will be the same because it only depends on the volume, and the volume is the same. So it will be the density of water, okay, times g times the volume. So the buoyant force is the same. That will not be the same, it's the mass. And this one has a smaller mass, so of course it's going to accelerate more. So the mass here will be the density of the object times the volume times g. Okay, so the net force is the buoyant force minus the weight, which is rho, v, and g, which is equals to the mass times acceleration. So this one has less weight, so it's gonna accelerate faster. Okay, so let's do the next one. So this one is more quantitative, less conceptual. So you can stop the video and try to do it. Okay, so first I need to be able to make anchor. I don't know what it looks like, something like this. So what's going on with that anchor here? You have the tension T. You have the buoyant force pushing up, which is the weight of the water displaced, and you have the weight here. Obviously, it's going to be the density is larger than the water, but you have the tension here. So Newton's second law, or equilibrium, you have the buoyant force here plus the tension equals the weight. Okay, and they want you to find the buoyant. They want you to find the tension. So the tension will be equals to the weight, and the weight weight is mass times G, and they are giving you the density, which is the density times the volume times G. So it's going to be rho, so density of the anchor times the volume times G, minus the buoyant force. So the buoyant force is the weight of the water displaced. And that will be the density of the water, seawater, times the volume is the same, times G. Okay, and what are we missing? We are missing G. We have rho, we have the volume. We do not have the volume. Oh, but we have the weight. Okay, so we have the weight. So 833, it's the weight equals the density of the object times the volume times G. That will be great if we can find the volume times G. So the volume times G is 833 over 7800. I'm going to plug that into here. So the tension equals, so rho here is rho V. I'm lost. So it's going to be rho. So this is Vg. So rho is 7,800. So 7,800 times, okay, we already have that. It's okay. Minus the water's 1025 times 833 times 7800, right? So it's going to be, I can factor out here. So it's going to be 1 minus, is that 23 or 25? 25 over 7,800. So you should be able to do it better than I'm doing it, right? It's a little bit confusing. But if you get that, if you do the computation, you can simplify, right? You can say 1,025 is about 1,000. You can simplify this. This one, you can say it's 80,000. So you should try to simplify as much as possible. Okay, so this one, you can say it's 8,000. This one is 8,800 about. And if you do that, you get 724 Newton. Okay. Okay, next, I think the next one is the last one. I forgot what it is about. Let's look. Okay, so it's not a tricky question, but it's a typical question. So it says A and B are submerged. So gravity is 0.877. And the density of B is 1/3 of A. Okay, so it's a nice problem because it's typical. So submerged, okay, you can think of that as being at the bottom. So it's submerged here. And they are talking about the gauge pressure. And the gravity here so you have the fluid here, which is density of the fluid is 0.877 gram per cubic centimeters. And the density of this one is 1/3 the density of A. But they are talking about the gauge pressure, which is the hydrostatic pressure. But the hydrostatic pressure is rho of the fluid, G, and delta H. So you see, it does not depend on the density of the object. So if they are placed at the same depth here, it's going to be the same hydrostatic pressure, the same gauge pressure. So the answer is 3, and you didn't have to use the other information. Right? I think it's that what the yes, that's the last one. I hope it helps.